So we have Lukáš here. Hello, Lukáš. Please, a round of applause. He's going to tell us something about generators and everything we should know about generators in Python. So, Lukáš, off you go.
Can you hear me in the back?
No. Oh, wait, it's off.
Is it?
We can do a bit of talk. Pop, 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 pop. Try it.
There we go. How about now? Can you hear me? Okay. So I'm here to talk about generators in the terms of Python education, because all of us hopefully are here to learn something, right? So I learned Python by myself, mostly from online resources, right? Like online courses and documentation and online videos and such. And generators are probably one of the most neglected Python features from these courses, because people who usually do these are mostly entrepreneurs, people who don't probably do a low-level programming, things like that. So they basically tell you how basic generators work and that you feed for loops with them, and then they move on to the next topic. So what I'm about to try to do here is go over some features and go over them in a way that is, in my opinion, kind of the optimal way for learning, better than just listening them. Basically what I'm trying to do is go over them better than the watch module lady, okay? So this talk is not project-oriented, right? It's not, it's not hands-on, technical, practical usability, nothing like that. And we might go a little too far at some points, right? So apologies. Okay, so we start with the iteration, right? When you start learning about these, you know that every single object that supports iteration may support it in a very different way, right? So if you drive some object with a for loop, for example, a dictionary, you get keys. So that's why we usually use the items method for separating keys from values. If you use strings, you iterate over individual characters. If you use files, as in the actual file object, you get lines of code, okay, or lines from the text file, right? So that means that whatever those items are, right, the iteration protocol stuff that drives them is implemented on the side of the object itself rather than the for loop, okay? Because different data types implement this in a different way. So what is this mechanism and how do we use it? So this is basically how the for loop works. You transform, or you get an iterator from the object you try to iterate through, right? Because the for loop doesn't iterate over the original objects or containers by themselves, right? That you need to kind of get the iterator object there. And then you call next on the iterator, and every next call will give you the next value, right? Until the sequence is exhausted at some point, in which case the stop iteration exception is raised. That's it. Right? This is basically the for loop. Okay? There's nothing else going on the side of the for loop that you should know about or should care about. So this is the basic abstraction of that, right? We can see that if we compare it to the actual for loop, it's basically the same. It's just a shortcut for whatever is here, okay? So that's how stupid the for loop is, okay? Now, what if I wanted to create an object that I'd like to iterate through, but with my own sort of pattern in mind? So to create an iterator, all you have to do is implement methods that can be used with the object when you call iter and next, right? So that you can feed for loops with it, right? So if I create my own countdown object, right? The whole logic of the countdown is here, right? Every time I call next, this function gets executed and it gets me the next value, okay? That's it. The iter method returns itself, or returns the object itself in this case, because I'm already implementing the next call right? Usually what you could do for your objects is to put something in here that returns an iterator, right? But we already have an iterator, so every iterator needs to return itself with the iter method. That's kind of a, that's kind of a workaround around that. So what if we don't implement the iter method? Well, it turns out that you cannot feed for loop because the for loop thinks that your object is not an iterator anymore, or iterable actually. But you can still call next, right? So those things aren't really connected to each other. Okay, so that's kind of neat to know. Also, important to know, if your object contains getItem method, and you support calling with numbered indices, that's what will get used instead, okay, by default. So beware of that if you support getItem. Okay, so things about these weird objects. This one that I have right here, this countdown, is fairly simple, but I'm referring to some sort of its state multiple times during the execution. And if this object was a little bit more complicated, this can get really exhausting really quickly, right? A couple more of these and this code is even longer. You need to manually and explicitly support iteration, right? Or adhere to the iteration protocol, right? That's kind of weird. And you need to put a base condition with stop iteration in there somewhere. So, because otherwise the for loop doesn't know it needs to end at any point, right? So these things are not necessarily bad things. It's just inconvenience on my end as a user, okay? So if we try to, use generator instead, all of this goes away from me, because maintaining the state is basically just local variables because you define generators as functions, right? The iteration protocol is handled by the yield statement, and the stop iteration is kind of not visible anymore because whenever this function returns, that's when the stop iteration is raised, right? So the stop iteration is basically handled by the return statement at this point, okay? So that's why generators are more convenient ways of doing this sort of thing. So let's talk about the function definition. We define generators as functions, right? So let's explore functions for a moment. You find out that whatever this thing returns here, you always get a generator object, and the way that Python knows that this is it's supposed to return the generator object is because it contains a yield statement. If you put yield anywhere in your function, okay, your function will return a generator object, okay? And the way that you actually, as a user, can find that out is by, asking the code object for its flags and separating the 5th bit. It's kind of, it's kind of low level here. If you want to know more about flags, or your functions, basically. So as a beginner into Python, of course, what you do is to run disassembly on it. And that's the generator right there. That's the flag. That's the flag I'm looking for. That's the flag that gets set by the compiler if the parser finds a yield statement somewhere, okay? So that's how the function knows it's supposed to return the generator. If you want to see all these flags, I do recommend checking the compiler flag names, because that will give you some headaches to figure out what is what. And if you feel really exploratory, you can always look at the source code, right? It's not very well documented, however, so you have to do your own digging. So what is this yield statement? The best way to learn how a keyword operates in Python, in my opinion, is not to search on Stack Overflow and asking how it works. It's finding out what it actually means, right? Because all of these are in English, so you look at the definition in English, and it tells you that yields produces something or gives way to something, okay? So let's explore that, right? So we have the yield statement. If I hit the yield statement, what happens is I get the value, right? So it produces something and then suspends the function execution, right? So it gives way control to me as a caller, okay? So that basically, so this right here actually describes the yield statement pretty well. If you ever get lost, you'll always look at the English dictionary. So what you have here, basically, generators are resumable functions, okay? At this point, I probably should tell you about optimization and the fact that resumable functions are less expensive on resources than, making a new stack of, when calling new function every time and so on and so forth. I'm not going to do that because nobody really cares as a user at this point. And then the return statement. I told you that the stop iteration is handled basically by the return statement. Turns out you can actually use return statement in a generator. And if you actually return some value, it gets carried inside a stop iteration in its value attribute, right? So the way you can extract that return value is like this. Basically accept the stop iteration, and then you get the value, okay? This is completely ignored by the for loop, by the way. So you do have to do this yourself if you're doing this. And then we come to the actual function suspension functionality inside a generator, because we've already talked about producing values, and nobody cares about that. I mean, we all kind of know about it and how it works, right? So let's talk about the function suspension. And this example is kind of stupid, but let's pretend for a second that the open function doesn't return a context manager, right? So we have to make our own. So what we do, using a generator, we actually, using the yield statement, we split the function into two, into the sort of the enter context and exit context parts, let's call it, right? And what happens then is that when I call next, I basically enter the context. Whatever happens outside of this generator then, because when you yield, you give way to the caller, you get the file, so that would be your context. And then you call next again and you clean up, okay? It's kind of creepy to do it this way, right? To use iteration basically to drive, context management. But this is where the cringing part starts, because you can actually use for loop to drive it, okay? So I wouldn't recommend that, but it's kind of fun. Use a for loop. If you've seen something like this before and you don't know where, it's because, of course, this is a very, very, very bad re-implementation of a context manager in Python. Okay, so in Python, you have a default context manager decorator that you can apply to your generators if you write them in this way and for this purpose. And but because we're learning here, of course, you as a learner, you'll try to implement it yourself, right? So this is how it looks like. Okay. So again, as with the for loop, you basically unlock the with keyword for your object with these special methods, right? So the first method is enter method, which executes the first part of your generator, right? Calling next. And then the exit method, which continues your generator execution, and your generator will clean up. Okay, that's about it. The actual context manager in the standard library is a little bit more complicated than this because it actually deals with some really weird edge cases, right? But for what I'm showing you here, this is more than enough, okay? So this is one example of the function suspension abuse, let's call it. This is another one, and this is even more stupid. You get this generator which yields until a certain time expires from its initialization, okay? So you have this weird object where you keep calling next, and you're basically, it's this like, are we there yet kind of, approach where you're asking, well, can I move on? Can I move on finally? So you have this base condition that basically locks your your progress within the program run. It's kind of weird to think to seeing this, but you can use this as an example of anything that you're waiting for, right? You can wait for some stupid packet to show up on your socket. It's basically the same principle, right? But the problem with this, even though I told you before that the generator is a simple version of dealing with iteration, this is not an iteration anymore. Okay, you're not producing values. You're not really, doing anything repetitive. You're basically halting the execution until some base condition is satisfied. And this actually sometimes may require some kind of difficult initialization or more complex initialization. And in this case, I would actually advise to go for a more pragmatic approach, which is separate the initialization from the actual logic, right? This may look nice. It may not. It can look even more nice, right? You can do basically whatever with this because you have now you have your own custom type. Okay, so you can do anything. If I wanted to make it more user-friendly, I could do something like this. And this is the moment I realized how stupid this example is. Because just look at this. Right? I'm almost causing atrocities here. Okay, so this is another alternative way to define a generator that's going to be used in some sort of a for loop or anything that that implicitly tries to create an iterator from your object. Right? You just implement it inside the iter method, and then use your class as a base object for this. Okay. So now more on the yield, because we're not done with the yield. Okay. The yield expression can actually be evaluated. Okay. If you start learning about this, it may not be this obvious, but if you do something like this, what's going to happen, right? And how you use this is, whenever you yield, again, you give away control to the caller, but because of how assignment operation works, the right side needs to be evaluated before the value gets assigned to the left side, okay? But because this right here suspends the execution, it's not really evaluated, right? And the way you evaluate it is that you basically send stuff into it, okay? So you use the send method of a generator to basically evaluate the yield expression to something, right? So basically, at this point, item assigns to hello, and because I'm returning it, you get the hello at the end. Okay? That's how that works. Objects that you send stuff into, right, are called coroutines. So basically, generators implement this coroutine functionality to them. This may or may not be useful to you, depending on how you use it. This almost never gets covered in like online tutorials. Like if you buy some stuff on, I'm not going to mention all those sites, but yeah, you know what I'm talking about. Yeah. Okay, hopefully this is clear. I'm not going to spend any more time on this because it's going to get really complicated. But basically what it shows you is that generator objects actually have their own methods, right? And you can do stuff with them more than just calling for the next item in the sequence. And so these methods are close, which basically raises generator exit. Now this generator exit basically ends the execution of the generator sort of prematurely before stop iteration, right? You can do it manually by calling close. Send stuff into the yield statement and evaluate it into something, into whatever you're sending into it, right? And throw is kind of a combination of both. Like you are sending stuff into it, right? But the thing you're sending into doesn't evaluate, but it raises, right? So you throw in an exception, which gets raised at the yield statement. And I've also included this yield from descriptor down here because it kind of foreshadows what's about to come. I'm wondering how many of you do not understand this sentence. Okay, that's great. Some of you. Well, being iterated by yield from. Like, what in the world? Okay, so the yield from expression is kind of more complicated. This is where things get a little bit more complicated, because what the yield from does, if you try to use it in the way it's prescribed in the documentation, the documentation will tell you that it delegates iteration, but it doesn't tell you what it does with the iterator here, because I'm basically sending in a sequence of numbers. It automatically transforms them into iterators, because otherwise it couldn't iterate over them. But it also handles the stop iteration. Okay, so now I don't have to deal with that. Okay, I don't have to deal with the stop iteration anymore. The yield from expression deals with that for me. But it gets even better than that, because if you use generators, you use stop iteration to basically get the return value. Okay, so if I use a generator there, what's going to happen is this whole yield from delay expression is going to evaluate as the return value from the delay. Okay? I'm going to slow down here. You create a wait generator. You keep calling next. When you keep calling next, you yield from delay. Delay works in a way that unless the base condition is satisfied, you are not moving forward. It will not let you, okay? So you're calling next, and you're trying to get somewhere, and at some point, after those 10 seconds, you get the value, and because you're using yield from, this whole expression evaluates as the return value from delay, which is the time it took for you to request the value. And again, just as before, gets assigned, and then you print, and then move forward, right? So the yield from actually allows you to call the generator almost natively. Like it's almost a call, it's almost like a function call, but not really, right? So that's the yield from. I'm wondering how many of you have never seen this before and are confused about it. Great. I am doing something helpful here. That's great. Show me again, how many of you are actually confused? Seriously? Okay. I'll be around. You can ask me anytime. I'll launch the interpreter. Okay, I'm actually going to answer some questions because we have way too much time. How do you feel about using, okay, so how do you feel about using multiple yield points to implement finite state machines? Okay, now who asked that? Seriously. Show me your hand. I feel like you're trolling me. Was it you?
I asked.
Okay, so, finite state machines. Well, I have no good answer to that. Because normally I'd say I don't have feelings, but that's kind of, using multiple yield points. Fine. Jesus Christ. Okay, let me think about it. Let's move on. Can you give us some example where generators simplify or completely replace some of the design patterns popular in other languages like Java? Yeah, I would have to see which design patterns you mean. Like the design patterns that generators replace, I don't think that they actually replace anything. In my opinion, they just add, more options for you, right? In terms of concurrency, for example, right? Python async framework. Well, completely. They are completely connected. I'll talk about that in a minute. Is the generator flag on function specific to CPython or part of the language language spec. I don't know. I have only seen it in C Python in the source in the header file for the code itself. So I'm not sure, but I'm guessing. I don't know. I don't have a way here to see in other implementations. So maybe you could tell me. Good. Yield from. Let's go again. Yield from. You delegate iteration, right?
I just have a comment. Someone, regarding the question about the design patterns in other languages.
Okay.
So this statement is implemented by generators, and that replaces, for example.
Wait, what? I'm sorry. Sorry. What's implemented by generators?
Okay, so I just wanted to say that someone asked if generators help replace some design patterns from other languages. So generators replace RAII from C++. This is done using context managers in Python, and you could say since they're implemented using yield that it replaces that.
Okay, cool.
Okay.
Thanks. Okay, this yield from stuff is very important, so let's go over it again, okay? It delegates iteration. What do I mean by that? I'm sending something iterable to a yield from expression, and if I call next on this chain object, I'm actually not calling next on the chain object, I'm calling next on this x right here until this x is exhausted. And then I move on in the function body, right? So then when I call next, I'm calling it on this y, and so on and so forth. And if you use a generator here, in this place, this whole expression evaluates, right, as the return value. And that's it. It's really that simple, right? Okay, so let's put everything together. You have the delay, you have the wait that returns the result from the delay, and because you're too lazy to ask for the next value yourself, you implement this function that basically runs it, okay? Now, you may have seen something like this before, and especially if you're working with Python 3.5 and more recent. And that's because this whole thing, what I was showing you up to this point, is precisely how async and await works in Python, right? So that's the answer to the form question. There is nothing else going on in the async await than this, okay? There is this await method that replaces the iter method, and then you use yield to, give control back. And it works exactly the same way. And the reason why it works exactly the same way is because you get this coroutine object instead of a generator, right? When you define function with the async keyword. And of course, we're learning, so disassembly again. You have new flag called coroutine, okay? And the coroutine flag works the same way. Basically, if a parser finds async definition, flags the function as coroutine, returns a coroutine object. And this coroutine object is very similar, if not exactly the same, as the generator as far as these go. Okay, so this is the actual diff from the help page, comparing generators and coroutines. You find out that actually coroutines raise generator exit to stop them, right? So this is kind of a natural progress towards using coroutines. But what is actually different is that they are not iterable, right? That's why I was using this send method to move the execution before, is because you cannot call next, you cannot implicitly convert them to iterators. All you need to do is return an iterator from the await method. And that's how it works internally. Okay? So let me go back. You can meditate on this for a minute. Right? So if you're doing some porting, that's it, right? And there is almost nothing else that I can say about the async await syntax, right? I've already explained generators somewhat. I've already told you about the yield from and the coroutine functionality, right? And that is basically everything that async await syntax deals with, okay? That's it. The reason why people usually fear async await is because of async IO. And if you look at the PEP for async IO, you will read it for 3 days constantly and will not remember anything because it's so darn long. And that is the reason why it's very difficult to grasp. And because, you know, people are, well, not forced, but people find it a good idea to explain async await using async IO library. This can get very difficult for people who are trying to learn it, you know, as opposed to actually use it, right? So we have coroutines and async await. So when you get to this point in your learning, right, in your learning journey, you start to implement your own task schedulers because you don't want to run your coroutines by yourself, right? You get some sort of task scheduler. Don't really mind fixing my errors here because this is not really a task scheduler. It's more like a side effect generator, I would call it maybe. But yeah. So this is what you do as your first day of async framework programming, and what you find out that it's actually really easy to build something that will drive your coroutines, and actually it will drive them, all of them, kind of at the same time, right? So this is how concurrency works, or cooperative multitasking using coroutines, I should say. You send the coroutines into your scheduler, and your scheduler runs this stupid loop here where it takes a next coroutine from a queue, sends a value into it because you can't really call next, and then if the coroutine is depleted, raises stop iteration, or actually just does nothing actually, or maybe return a value or a callback or whatever you attach to it. Otherwise, call for the next step and then return it to the queue, right? So you get multiple coroutines running at the same time in one thread, in one process. Okay, so this is how you get rid of multi-threading and multi-processing in your application. This is a sort of alternative, more down to earth way to do it. Okay. So when you become proficient in that, then you start reasoning about async, and you start reasoning about it in a way that you start convincing others that it actually doesn't matter what do you use with async await syntax, because this basically does the same thing. That's for me as an observer of the behavior of my program. If I use this, basically does the same thing. I would actually argue that my delay function is better because I can specify the wait time in a more humanly way. And then you say, well, it doesn't even matter which task scheduler I use. Right? I can use async IO get event loop. I can use Twisted or anything else, or I can use my stupid own coroutine scheduler. Where I care, right? And then you find out that if your program drives something like this, you only continue using coroutines from this point, right? Because your whole program is basically running on this stupid scheduler, right? And the thing to remember about this is that there is a yield somewhere buried at the end of the await chain. Right? And that's the point of the switch. If you're trying to do I/O programming, this gets really, really complicated because with I/O you have to go all the way down, and you have to create awaitable objects which which call, kernel traps and things like that. Like if you're trying to re-implement socket, that could get really weird really quickly and really advanced, right? So this is the point where you don't deal with generators anymore. Okay, kind of naturally come out of it. So let's recap. Start with built-in iterables, right? Kind of cool. You learn about the for loop and the iteration and how it works. You start building your custom iterators, okay, to drive the for loop in the way that you want it to be driven. Generators and coroutines. This is where you start feeling kind of powerful, because now you're not only changing how the iteration works, but you're implementing your own iterating pattern, which can branch and can do all sorts of things. You can send values into iteration, right? Which is kind of amazing. The yield from is really the gateway. Like, learn about yield from. Take good precautions to know how exactly it works. Which will directly move you to awaitables and native coroutines, which was what I was talking about just now. And the last step, and this is where your coworkers will start hate you, iterable coroutines and asynchronous generators. Now, that's magic for me, okay? Because what this allows you to do is to put async in front of everything, okay? You get async for loops, you get async context managers, you get async everything, okay? So if the code, I guess that's, I'm not gonna elaborate on that, probably good idea, right? So if you're learning about generators, I would advise you use this scheme instead of, the classic approach of, oh, let's talk about this feature in this video, and it's going to be 5 minutes, and then 5 minutes next feature, and so on and so forth. Okay, this is way better because this kind of naturally falls into one another. So I guess that's it from me, really. Keep learning. Thank you.
Works. Okay, thank you very much for the talk. We have a few questions, so you have time.
Yeah.
So let's start answering.
Okay, interesting. Chain is basically for a for loop yielding args, or is there more to the standard library? Which chain? This chain? Who asked that?
I did.
You did?
This chain.
No, did you really?
Yeah.
Yeah, okay. So, did you mean this chain?
Yeah, I meant that chain.
Okay.
It's a really basic chain.
Yeah. For a for loop yielding args.
So I'm thinking if this is how the standard library implementation works. From Ether tools.
I don't know, actually. It might.
Right.
It might, actually.
It makes sense that it
Yeah.
does.
Like, if you don't know how something works, try to implement it yourself. And if your implementation works, there's a good chance that that's how the standard library stuff works. Okay, it's the same with the context manager here. Like, this exit method should be, should handle some edge cases and should be really more complicated. But in its core, this is how that context manager decorator works, right? It's the same thing. What's next? What happens on the next on the yield from basic example? Does it raise stop iteration or just yield? Probably, yeah, wait. You mean here? If I call next again down here, you raise stop iteration from the chain because it's a generator and I'm not handling that in any other way, right? So naturally, stop iteration again.
Okay, if you have a follow-up, you can raise your hand. Right?
Have you worked with some of the async web frameworks like AIO, HTTP, or SANIC? Is AIO HTTP actually a web framework? I thought it was just async implementation of a request or something like that. Does it actually include?
It is now, yeah, they expanded it. It has a server component now.
Oh, really? What's running it?
Wait.
Not sure. Haven't used it myself.
Yeah, we might have to repeat this conversation again with the mic.
So I just said that AIO HTTP now also has a server component. They added it start of this year, I believe, or last year.
Okay, and what's driving it?
I'm not sure.
Okay. We'll find out. Tornado? Can we get the mic to the person?
Find what's the optimal.
So Tornado web framework does the async await and everything else.
Oh, yeah. But the question was, I was asking if the AIO HTTP actually includes some sort of.
Yeah, but he said that.
Oh, but it includes Tornado actually.
No.
Or-
It doesn't. But the Tornado already does it.
Use the mic.
Before this started.
Oh, yeah. Of course, sure.
I have one question.
Okay.
The drivers for databases and stuff, they don't follow this, or they follow this. Do you know anything about it?
Drivers for databases? You mean
Yeah,
like asynchronous libraries for
Yes.
databases?
Yeah.
You should look at the AIO libs project. It has like AIO Redis, AIO. I think SQL is there somewhere, right? AIO libs.
Okay, thank you.
Postgres has a async implementation of the driver.
Okay, another example showing async IO code. Create task after run forever. Will this actually work? Execution not progress past the run forever.
To speed things up, raise your hand if you ask this question.
You mean here? Create task after run forever. Will this actually work? Yeah, what I think. Actually, I wrote this some time ago. I think the run forever runs in its own like separate thread, so it doesn't block.
So this will work, and the tasks, the coroutines, will end up being executed.
Yeah.
So it doesn't block. It doesn't block on run forever.
No, because it runs in its own separate thread.
Uh-huh.
The same way I'm using it here, right? I just launch a thread, and it runs inside of it. But because I'm passing it this self-run function, which has a reference to itself, it can communicate.
Okay.
Really? Does it?
Yeah, I think so too.
Does it?
It does block. SNKIO does,
Okay.
does block.
Well, mine doesn't, so it's better.
Awesome.
Is it a syntax error to have yield or yield from expressions in async function? Actually, I think so. I'm not completely sure, but I think so. Is it what?
It's not a question, it's a quote.
Oh, it's a quote. So are you making iterable coroutines? How are you making iterable coroutines? Oh, they're actually, I don't think if they're called iterable coroutines. Yeah, you have to look at the PEP, which expands the async and awaitables. Because I actually haven't looked at these objects before. I haven't looked at the asynchronous generators or how they implement it. I haven't looked at iterable coroutines. I don't know. I just don't know.
Okay.
Any other questions?
Any other questions?
Or shall we eat?
Are you
finally?
sure? Okay. Lukáš, I think that
Are you done?
verified. Okay.
Okay.
If there's no more questions, thank you very much for this talk.
Hi, I'm Lukáš, and I've had the pleasure of speaking at PyCon Balkan, which is a conference which is very well put together, very nice people, great community, and I'm having a very nice time here. Thank you for spamming me.